So I'll just introduce the speakers. So this is Anmol Kumar and Kumar Satyadarshi. They are UG third years and they'll be giving this talk today and presenting this paper by Boas and Widder on a theorem on finite first forward or backward differences. This is derived purely from first principles, but it's very involved, so they might have to go fast at some points. So if you need clarifications, please feel free to ask.
Thank you. So, first we'll make a few definitions because the theorem itself requires you to know some definitions. So, we start with defining the kth forward difference of step size h. This is denoted by delta kh, and for a function f, this is at the point x, this is defined to be this is defined by this recurring formula. So, and delta 0 of any step size is defined to be the function of itself. So, these two, this recurrence gives you the formula for the kth forward difference of step size h, and note that this you can use to, this looks like the binomial formula. So when you suppose you have, for example, step size 1, then you can write it as f of x plus h minus f of x. And now if you take k is equal to 2, then that will give you delta h1 f of x plus h minus delta h1 f of x, right? And now you can substitute the first forward difference of step size h with this, so you get f of x plus 2h minus f of x plus h. This is for this, and then you have minus f of x plus h minus f of x. So this gives you f of x plus 2h minus 2 times f of x plus h, and positive f of x. So this looks like the binomial formula, and one can prove by induction that for any integer h greater than 0, we have so this is the general formula for the kth forward difference of step size h. So now the theorem, so I should write the theorem. So the Boas Widder theorem so suppose you have a function f defined on the interval a comma b. So this is the open interval a comma b, and you take any positive integer a greater than equal to 2, and you can define this interval I to be a comma b, and there is a hypothesis which this function satisfies, and we shall call that hypothesis for the rest of this talk to be hk, and that hypothesis is f is continuous and has kth order forward differences of step size h. This is non-negative. So, which is to say that delta h k f of x is non-negative for all x such that the points, all the points which are being given as input to this function are in this interval a comma b. So you cannot, this function is defined only on I. So you need to make sure that when you write this equation, since you are replacing x by x plus j times h, so you need to make sure that all these quantities x plus j times h are in this interval a comma b. So just this condition is there, and it amounts to saying that, and also the step size is positive. Okay, so it amounts to saying that this holds because the smallest input will be f of x. The smallest input will be x, and the largest input will be x plus k times h. So both should lie between a and b. So this is the theorem. This is the hypothesis of the theorem, and what this theorem tells you is that if you have a continuous function with this holding true, then we have that the k minus 2th order derivatives are defined. So the k minus 2th derivative exists and is continuous and has non-decreasing So this is what the theorem says. If you have a function defined on an interval, open interval a comma b, then the k minus 2th order derivatives exist, they are continuous, and it does not say anything about the differentiability of the k minus 2th order derivative. It just says that the k minus 1th order derivative, I shouldn't say it as k minus 1th order derivative. It just says that the left hand right hand derivatives of this function, the k minus 2th order derivative, are non-decreasing. So this is the theorem, and this theorem can be seen as a converse of the Cauchy mean value theorem. So suppose what would the converse be? The converse would mean that if you have a function such that all its kth order 1 through kth order derivatives are non-decreasing. So that would mean the derivatives are non-negative, right? So suppose we have a function for which fk at x is non-negative, then that would mean that the kth order forward differences are also non-decreasing. So this is the usual theorem. Suppose you have for k is equal to 1, you can like derive it from Lagrange mean value theorem, right? But the converse doesn't say anything about the kth order derivative. It says something less. It says things about the k minus 2th order derivative. It exists, it is continuous, and it has non-decreasing left hand and right hand derivatives. So the next.
What happens if f of x equal to x square and k equal to 2? Isn't it?
F of x is equal to x square and k is equal to 2. Yeah, so the kth order forward difference, suppose you have step size h, and you take this to be f of x plus 2h, which is rated x plus 2h whole square minus 2 times x plus h whole square and a positive x square, right?
Yeah.
So this will be x square cancels out and 4x square. So a 2x square.
2x.
That's all.
So like this is satisfying the hypothesis.
Yeah, this is always non-negative, right?
So but it doesn't satisfy the. It is not non-decreasing, right?
No, but the for k is equal to 2, the k minus 2th order will be just the function.
And x square is not non-decreasing. It does decrease. Derivatives are not.
What is the question? What is the question?
No, like I took
No, but the derivatives are non-decreasing, right?
Derivatives.
Not the function itself. So the derivative would be at any point you see. The derivative would be a straight line that has non-negative slope. So this theorem holds for k greater than or equal to 2, but we shall see that it also holds for k is equal to 0 and 1 if we interpret it correctly. So I can write.
No,
I can do it now. Won't take time. So for k is equal to 0 and 1 it holds. So for k is equal to 1, suppose for k is equal to 1, so the function satisfies h1. So the theorem would say that the function is continuous, defined on a comma b, and it has the first order forward differences are non-negative, which amounts to saying that f is non-decreasing, right? So the function is non-decreasing, and you have what you want to prove is that f minus 1. So we can define f minus 1 to be the antiderivative of f, right? So we define f minus 1 to be the antiderivative this quantity. So this function is defined to be f minus 1 at x, and the c can be anything between a comma b. You need to fix a c. So what the theorem says that the function f in f minus 1x is continuous, and that is true because it's an antiderivative, so it's always continuous, and it has non-decreasing left-hand and right-hand derivatives. So the derivatives of this function are precisely f. So and we have that f is non-decreasing. So this holds. And for k is equal to 0, we have that the second order antiderivative. So the second order forward difference first. So we have
zeroth order forward difference.
oh sorry, yeah, zeroth order forward difference. So the zeroth order forward difference as defined is f, the function itself. So that is non-decreasing. So we have that fx is non-decreasing.
Fx is non-negative.
Fx is non-negative. Yeah, fx is non-negative. So you can say that the antiderivative this function is non-decreasing, right? because this function, okay, this function is non-negative. If you integrate it, as long, as you increase x, you're adding some more positive area. So this function is non-decreasing. So this antiderivative, the second order antiderivative, can be seen as the antiderivative of this function, and this is non-decreasing. So by the first part, we have that since this function is non-decreasing, the one inside this, we have that the second order antiderivative is non-decreasing, right? So this holds. Any doubt? Okay. So we shall now prove the theorem. So the theorem, the proof of the theorem proceeds via induction. So we first prove this theorem for k is equal to 2, and then the induction step is this is the last lemma in the paper. So the induction step says that you prove this theorem for f prime.
For k is equal to -1, and
Yeah.
we
K is equal to minus 2.
wait. Like if you define h, you are defining the k order.
Yeah.
No, I'm not asking you. Forward difference are 0.
Fine.
No.
Okay. So the proof of this theorem proceeds by induction, and we assume this theorem to hold for k minus 1. So whenever a function is defined on an open interval a comma b, and it has the property hk minus 1, then we assume that f of the k minus third the k minus third order derivative has those properties. It has non-decreasing left hand and right hand derivatives. So we assume this, and we use this to prove the induction step. So what we prove is that when f satisfies hk on a comma b, then in fact f prime satisfies hk minus 1. So this is what we prove, and what we have assumed is that for any function satisfying hk minus 1, we have that the k minus third order derivative, which will be the k minus second order derivative for f, right? The k minus third order derivative for f prime is the k minus second order derivative for f. So that function fk minus 2 at x for any x in that interval, that quantity exists, and it is continuous and has non-decreasing left hand and right hand derivatives, which is what we were supposed to prove for the function f satisfying hk, right? So that was the entire thing we had to prove for f satisfying hk on a comma b. So the induction step is like induction step we do by proving that f prime satisfies hk minus 1 on a comma b, right? Okay. So to prove f prime satisfies hk minus 1, first of all, it suffices to prove that if f prime satisfies hk minus 1, it's done, right? We just need to prove for k is equal to 2, so that the base case is done, and once we do this, we are done. So first note that so the rest of the lemmas, the 13 other lemmas, will be to prove the existence of f prime and the fact that f prime satisfies hk minus 1, and to prove that if and to prove the theorem for k is equal to 2. Okay, so firstly we want to show that f prime satisfies hk minus 1. So we assume the existence of f prime, and we first prove that f prime satisfies hk minus 1. So what should be the idea? So f prime is a limit, right? F prime is a limit epsilon goes to 0, f of x plus epsilon minus f of x upon epsilon. And this can also be written as limit epsilon goes to 0, delta epsilon f of x by epsilon, right? So we want to prove that the k minus 1th order forward differences for this function is non-negative, right? So we need to so for any k greater than 0, we need to prove that delta k minus 1 and this function f prime of x is non-negative. So you see that you can take this operator inside this limit and write this as you can write it like this. Okay, so you want to prove that this is non-negative. So here the step sizes are not equal. So this motivates the first lemma. So what the first lemma says is that I shall write it down. But the first lemma proves that if you have a function satisfying hk on a comma b, then instead of choosing a particular step size k and using that equation and saying that it's greater than equal to 0, you can in fact choose k positive real numbers, delta 1, delta 2 through delta k, and say that this quantity in any order, this is non-negative. So the step sizes need not be equal. So the first lemma is this, and it's motivated by this. What you need to prove is that this function is non-negative, and here the step sizes are unequal. So we shall prove it, and you know that this function satisfies hk, right? So we first prove it for we first prove the lemma 1, which says that you can replace the number k and equal step sizes by unequal step sizes in any order. So also note that this operator commutes. So this operator commutes. So what it amounts to say is that this holds. Right. This is easy to see. So that is why the step sizes can be in any order, and so now we prove the first lemma. So we have the function f satisfying hk in a comma b, and we take real numbers delta 1, delta 2 up to delta k greater than 0, and this implies that for any choice of these positive real numbers, we have this quantity is non-negative. Okay, so And again we have that condition that the inputs to this function, because again your inputs are changing, like first you input x, then you input x plus delta 1 up to x plus delta p. So all those inputs should lie in a comma b. Okay, so this is proved by induction. So what we prove is that if f satisfies hk, then we have this quantity is non-negative. So first note that once we prove this, we'll be done, because we assume this theorem for k minus 1. We assume this lemma for k minus 1. So when the function satisfies hk minus 1, we can take unequal step sizes and say that this holds. So this we can, since it's commuting, we can say that this quantity is non-negative, and then we can choose a k minus 1 distinct or k minus 1 positive real numbers, delta 1 to delta k minus 1, because we know that for k minus 1 this holds. So this proves, this is the induction step. Here the step sizes are arbitrary. So it amounts to showing this. So what we do is we take this function fx and we take the first order forward difference, and that will be f of x plus h minus f of x, right? And then this can also be written as f of x plus h minus f of x plus this is h plus n. So this telescopes, right? This cancels off all the way to, and only this is left. So this thing is equal to this. So we can write this more neatly as k is equal to 0 to n minus 1 delta h upon n this correct, right? Yeah, you can write it like this. And now what we do is yeah, so we have delta h f of x is equal to I is equal to 0 to n minus 1 delta h upon n f of x plus I times h upon n. And we can apply this delta operator, since we want this k minus 1 times, we apply this k minus 1 times to write of x is equal to right. We have this.
I don't see
What
how.
is I?
What is?
I.
Okay, sorry. This I is the summation of all these I1 through Ik minus 1. So,
She's right here.
so you can see this as we first had this. We apply another delta h. So that gives you this function and another summation. You pull it, right?
Okay.
And call the index j, and j varies from 0 through n minus 1, and you have inside this you substitute f of x plus jh by n, right? And inside, when you substitute x plus jh by n, this becomes x plus I plus j times h by n, right? Is this fine? So you can repeat it. This fine? So I can write one step. So suppose you do this twice, then you'll have you take us, because this is defined in this way. I mean, this is equal to this. So you have j is equal to 0 going all the way to n minus 1, and inside you substitute
Delta H by N of
inside you substitute this quantity. So this quantity, you have this function, right? This is still here. This is the, when you impose another delta h. So this is this quantity, and then you plug in this quantity inside delta h, right? So that becomes delta h by n f of x plus j h by n plus I h by n, because you're replacing x by x plus j h by n, right? So this is the same as j plus I h by n, and you do this k minus 1 times to get this, fine? Okay. And so now we have this. Now we can take another delta, and this time the step size we take is h upon n, because we know something about the kth forward difference. We know that it's non-negative. So this does not help. We take another delta h upon n, and this becomes delta h upon n, the kth forward difference, and that we know is non-negative. So now we have delta h upon n, delta h k minus 1, f of x is equal to fine. And we now know that this quantity is non-negative. So this sum is non-negative. Okay. So we have that. delta h upon n, delta h k minus 1 f of x is non-negative.
For all n. For
So-
all n.
Yeah, for all n. Yeah. So you can write it as delta h k minus 1 f of x plus h upon n is greater than equal to delta h k minus 1 f of x, right? Because when you take it to this side, the difference is non-negative, like that. So you have this, and again you can replace x by x plus h upon n to say that x plus 2h upon n is greater than equal to f of x plus h upon n. And you can do this m times here to get m times h upon n n minus 1 times h upon n. So we have this, and now we can
How did we save this first time?
first time, yeah,
Again.
when you take this to this side, it's a difference, right? And that is non-negative. Okay. So we can add these quantities. Okay. Or you can say that this is greater than equal to this one, right? Because this is greater than the previous one and all the way to this quantity. This holds, right? And now you can, because you wanted to prove this for arbitrary epsilon, you want your m by n times h to be close to epsilon. Now you can choose sequence of integers mi and ni such that the ratio mi upon ni converges to epsilon. Mi upon ni times h converges to epsilon. We can choose such integers, such sequence of integers, and then we can say that delta h k minus 1 f of x plus epsilon is greater than equal to delta h k minus 1 f of x. Note that we are imposing the limit. We can replace this by mi upon ni first, right? And we are imposing the limit I tends to infinity both sides, right? And this limit can be pulled inside the function because f is continuous. So here is where you use the property that f is continuous. And once you take the limit inside, you have mi upon ni times h converging to epsilon. So it gives you this, and this holds, right? So this is equivalent to saying that delta h epsilon delta h k minus 1 f of x is non-negative. Right. So this was the first lemma. So now we make a few more definitions, and we define, since we want to comment on the right hand and left hand derivatives, we define the right hand derivative at any point x as the limit h tends to 0 f of x plus h minus f of x upon h, and this is same as the limit h tends to 0 h inverse times delta h f of x, right? And similarly the left hand derivative
0 plus 0 plus 0 plus. That's turning to 0 plus.
h is positive, h is positive, okay. Now note that you can write this as f of x minus f of x minus h upon h, and this looks like a forward difference. So this is the forward difference at x minus h of step size h. So these two definitions are the definitions for the left hand and right hand derivatives. And now we move on to the second lemma, and the second lemma is very easy, and it says that if f satisfies hk in a comma b, then the functions delta epsilon f of x and delta epsilon f of x minus epsilon are non-decreasing functions of x. So wherever these quantities are defined, you need to make sure that the inputs are within a comma b.
Is that k minus 1?
I'm sorry. Yeah, you need to make sure that the inputs are in a comma b, and once that is done, these quantities are non-decreasing functions of x. So since f satisfies hk, we have that the k minus 1th order forward difference so we have this. Right, from lemma 1. And now note that we want to prove that this is non-decreasing. So choose some x and y such that x is less than y, and call this difference y minus x as delta 1. Okay. Now you can take this epsilon to be y minus x, right? And once you do that, this input becomes y, and this input is x. So you have proven that the function at y is greater than equal to the function at x, and that was what we had to do to prove that this is non-decreasing. The proof for this is similar, so I'll leave that. So now we have the fourth lemma. So before the third lemma, we see what the fourth lemma is. So the fourth lemma, and every lemma from now on till the sixth lemma, we have that f satisfies h2, not hk. So we'll do this for k is equal to 2. because we need to prove the theorem for k is equal to 2 as a base case. So we do this for k is equal to 2, and the the lemma states that so f satisfies.
Can our proofs for k equals 1 not work as a base case?
It can, but the proof for the base case as k is equal to 2 is what we use for proving it for for k for the general case. So these lemmas will be required in that proof. So
The
it's
inductor
better,
step.
yeah. So it's better to do this. So we have S satisfies H2 in A comma B, and then this lemma states that F prime plus and F prime minus exists and are finite. And non-decreasing on the interval L. So this is what we are supposed to prove, right? We need to prove that since for k is equal to 2, the k minus 2th order derivative is the function itself. So we need to prove that the function. So to prove the Boas Widder theorem for k is equal to 2, we need to prove that the function is continuous. But the hypothesis assumes that the function is continuous, right? And we just need to prove that the left-hand derivative and right-hand derivative are non-decreasing on A comma B. So this proof we'll do after seeing what lemma 3 is. So lemma 3 states that again the function f satisfies H2, and we have for any for any x belonging to A comma B, we have that this function h inverse times delta h f of x is a non-decreasing function of h. And here the interval is a minus x to b minus x, because you cannot go past that interval. So this lemma, so this is the difference quotient, right? And you need to prove things about this difference quotient. So we first prove that this is a non-decreasing function of h. So to do this, so since f satisfies h2, we have for any step size delta by n, we have this is non-negative all the way to right. So we first take h in this interval 0 to b minus x. Okay. The proof for the other part is very similar, so I'll skip that. But for h belonging to 0 comma b minus x, this is the proof. So we have this because f satisfies h2, and now we can again add these inequalities. So we can just telescope it to get we get this, right? We just telescope it, we add all these inequalities, and we get this. So now note that if we take the this is an increasing sequence of n terms, if we take the first k term, if we take the first m terms here, then the average of the first m terms has to be smaller than the average of these n terms, right? Because it's an increasing sequence. If you're leaving these quantities, then you're averaging something smaller. And all of these quantities are bigger, so if you have added those quantities also and average, then that would have given you something bigger. So we average this for the first m terms, and again the thing telescopes. So we get this would be m delta upon m f of x by m by m. Right. Again, you can again you can take this to this side, and again we choose integers, sequence of integers mi and ni. So you can replace these by mi and ni, and again you choose sequence of integers such that this quantity converges to epsilon, because you want to prove that this is a non-decreasing function of h. So for any epsilon less than delta, you need to prove that when you input epsilon, which is epsilon inverse times delta epsilon f, that is smaller than delta inverse times delta delta f, right? So you need to prove that. So here, if your sequence converges so that mi delta upon ni goes to epsilon, then we have that this quantity, which is delta epsilon f of x upon epsilon by delta is less than equal to delta delta f of x. And you can take this to this side to get what we wanted. And note that this quantity, since ni is greater than mi always, this quantity is less than 1. So epsilon is less than delta. So this condition holds, and we have proved this. This fine? So this was the third lemma. And now the fourth lemma, which actually proves that, the theorem for k is equal to 2. So for this, we need to prove first that these quantities exist. But we already have seen in lemma 3 that these quantities, the difference quotients, these are precisely the difference quotients when you take the limit, right? So the difference quotients are non-decreasing functions of h. And this you get when you take h going to 0, right? So it's a limit of a monotonic sequence. The difference quotients are monotonic, right, in h, and this you get when you take the limit h goes to 0. So in the extended real number system, which is when you take minus infinity to plus infinity, so when the limit approaches plus infinity, you call that as the limit is existent and is infinite. Okay, so that is the extended real number system, and so this sequence of numbers, the difference quotients at any value x, these difference quotients are non-decreasing. So this forms, as you vary h to 0, this forms a monotonic sequence, and this monotonic sequence has to converge, right, in the extended real number system, because it's bounded above by plus infinity, and every bounded monotonic sequence converges. So you have that in this, it converges, but you need to prove that it's in fact finite. So you need to show a finite upper bound. So this part is done, the existence part is done, and now you need to prove it's finite and non-decreasing. So for non-decreasing and finite both, you need to obtain an upper bound, and that we can do by taking real numbers delta and epsilon, such that epsilon and delta are both bigger than 0, and this holds, so that we need to prove that when we input something lower, the output is lower. So, and we can also take real numbers x, y, z, such that this holds. And we need to prove that this difference quotient is finite. So what we do is, since f satisfies h2, and since we have from lemma 3 that h inverse delta h f of x is a non-decreasing function of h, we have for this choice of x, y, z and delta, we have epsilon inverse f of delta epsilon f of x. This is smaller than. So we have chosen epsilon greater than delta, and also note that from lemma 2, this was a non-decreasing function of x also. So we have that this is less than equal to f of y, right? This was a non-decreasing function of x, and we have delta inverse, or you can say epsilon inverse delta epsilon f of x minus epsilon, because again it's non-decreasing in x variable, and then from non-decreasing nature in this epsilon variable, we have x minus epsilon. And since okay, this should have been something else. So we first use the non-decreasing in this step size variable to write this, and then minus delta, and then
Anmol.
They come with it. We have no notes here. Just right next to lemma.
okay.
After this, we will write each other.
Yeah, so we have this. This inequality is by the non-decreasing nature in both x and h variable, right? So we have this, and now note that once you vary epsilon to 0, or first we can vary delta to 0. Okay, so we take delta to 0, and this becomes f prime plus at x, and that is less than equal to epsilon inverse delta epsilon f of y, and this is now something finite. So we have shown an upper bound for this. So, and also note that from this we get f prime plus at x minus delta. So it's also non-decreasing, right? So it's both non-decreasing and finite. So we have proven this for k is equal to 2, right? Wait, this is minus from the definition. So this was to prove that the theorem holds for k is equal to 2. Base case is done. Now we can prove. Now the subsequent lemmas deal with proving some facts about these difference quotients that will be used in the proof for the general case. And the lemma 5 is if f satisfies h2 in a comma b, then f approaches a limit So we know that the function is continuous inside the open interval. But what this lemma says that is when you take the left, when you take x going to the left end, the left extremity, you have that the function still approaches a limit. But that limit may not be finite, but that limit is necessarily not negative infinity. So this is done by saying that since f satisfies h2, we have this. So we can say that delta f of x is a non-decreasing function of x, right? From the lemma 2. So this gives you. Since it's a non-decreasing function of x, so it as you take x going to say the right extremity, it's increasing. So it cannot be negative infinity, right? So this is greater than negative infinity, and you can expand this to write f of x plus delta minus f of x, and now you take x going to b minus. So when you take x going to b minus, since this is greater than negative infinity, this quantity has to be, this quantity cannot be minus infinity, because if this is minus infinity, this is something between a comma b, you are giving the input, so this is something finite. So this won't hold true. So this proves this lemma for b minus, when x goes to b minus. The proof is similar when x goes to a plus. So I leave that. And the sixth lemma is also easy. So here f satisfies h2 again. And we have if there are two statements to this lemma. The first statement is if f of a plus is less than infinity, then we define f of a to be f of a plus So what this lemma states is that Again, if you have this function satisfying h2, then if you have this condition, we noted in the previous lemma that this function approaches a limit, but that limit can be plus infinity or something finite. So if you're given that it's not plus infinity, which is to say it's finite, then you can define the function value at a. You can extend the definition to a, and once you define it that way, you have that this quantity exists and is finite, or it is minus infinity. It cannot be plus infinity. So consider the map h going to h inverse delta h f of x. This is a non-decreasing function of h, and this quantity, the limit, is a limit when h goes to 0 of this difference quotient. So it's as you take h going to 0, it's a limit of the sequence of functions, right? So again, it's a limit of a monotonic sequence, so it converges. So it does exist, but we are not commenting right now about the finiteness, but we can show that it cannot be plus infinity. So also from this only we can say that it cannot be plus infinity because it's a non-decreasing function of this quantity x, and you're taking the left extremity, so it cannot be plus infinity and then be non-decreasing, right? It can only be finite or negative infinity. So this lemma is also done. The second part of this lemma states that if f of b minus is less than infinity, then we can define again f of b to be f of b minus, and then f prime b minus will exist and is finite or positive infinity. So here it's positive infinity or finite. So the proof is again similar.
सत्ता कब तक खत्म करोगे?
मैं टाइमर लगा
कितना है?
25 हो रहा है 25 I'm not comfortable in Hindi. I'm not comfortable in Hindi.
I can understand.
मैं हिंदी में बोलता हूँ, ठीक है? किसी को कोई दिक्कत नहीं। तो ऐसा है कि सबको स्टेटमेंट समझ में आया ना? इसको स्टेटमेंट तो पॉइंट ये है, मैं यहाँ से करता हूँ कि फंक्शन जो है वो k सेटिस्फाई कर रहा है, तो ये प्रूफ कि अगर k इक्वल टू 2 है, व्हाट इज द कंडीशन? अब जो k इक्वल टू 2 है, मैं एक्चुअली क्या करूँगा ना, एक्स्ट्रा 6 6 लेवल दे, आई विल जस्ट गिव ओवरव्यू ताकि जल्दी से हो जाए, और मैं पेपर शेयर कर दूँगा, दैट इज वेरी इजी टू अंडरस्टैंड, एक बार मैं बता दूँ तो hk जो है, अब मैं कर रहा हूँ k ग्रेटर देन 2 के लिए प्रूफ करना चाहता हूँ, ठीक है? लेकिन मतलब मान लो फंक्शन f जो है वो h के सेटिस्फाई कर रहा है और ग्रेटर देन इक्वल टू 2, लेकिन अगर मैं अब इसको प्रूफ करने के लिए जिस तरह से फर्स्ट लेवल का जो यूज है वो यहाँ होता है कि अगर मेरा f प्राइम लेटर सपोज hk माइनस 1 सेटिस्फाई कर रहा है, so I am done. Why? F prime is the property of hk minus 1. Why I am done? ऐसा सोचो क्यों हो जाएगा, क्योंकि उसने शुरू में बोला था कि दिस इज वी आर डूइंग बाय इंडक्शन. सो अगर मेरे पास ये स्टेप है, दिस इज गिवन, और इसी का यूज करके हम प्रूफ करेंगे कि f प्राइम जो है वो hk minus 1 मतलब फॉलो कर रहा है, तो वी आर डन. ओके, तो इसलिए डन हो जाएंगे क्योंकि अगर इंडक्शन के हिसाब से मेरे को क्या प्रूफ करना है कि fk minus 2 के ऊपर हम कमेंट कर रहे हैं, तो अगर मेरे पास f प्राइम hk minus 1 फॉलो कर रहा है तो बाय इंडक्शन हम इसके k माइनस 3 पे वर्क कर सकते हैं ना।
मतलब थोड़ा सा बढ़ा दे थोड़ा।
ओके हाँ ठीक है सॉरी। तो अगर f के k माइनस 2 पे कमेंट कर रहा है तो f प्राइम भी एक कंटीन्यूअस फंक्शन है। अगर मैं प्रूफ कर दूं कि h के माइनस 1 फॉलो कर रहा है, इसके लिए हमें क्या क्या प्रूफ करना पड़ेगा? पहला तो कंटीन्यूअस है, दैट इज अ स्टेटमेंट, और जो भी प्रॉपर्टी है। तो फिर हम इस वाले फंक्शन को लेट्स सपोज f प्राइम को मैं g मान लेता हूं, ठीक है। तो फॉर g हम किस पे कमेंट करेंगे? g के k माइनस 3 पे कमेंट करेंगे बाय इंडक्शन ऑल दोज प्रॉपर्टीज फॉलोइंग। ये हर एक प्रॉपर्टी फॉलो कर रहा है। तो दैट्स व्हाई मैं कह रहा हूं कि अगर f h के फॉलो कर रहा है फॉर k given 2, तो जस्ट ये बता देना कि f प्राइम इज फॉलोइंग h के माइनस 1, वी आर डन। ओके, बट हमने क्या प्रूफ किया अभी तक? हमने ये अभी तक प्रूफ किया है कि H2 का केस अगर है तो हमें पता है क्या होता है। लेकिन अगर सोचो मेरे पास जो इंटरवल है ये B है, ये A से B, अगर मैं समहाउ एक सिंपल सा थॉट दे रहा हूं जो कि बेसिकली इस आगे का पूरा का बैकबोन है जितना भी लेमा है, कि मेरे पास फंक्शन f है जो h के फॉलो कर रहा है, ठीक है। ओके, अब एक बहुत बढ़िया सा चीज होता है, अगर फंक्शन f h के फॉलो कर रहा है तो देयर एग्जिस्ट अ c, मैं क्लोज ले रहा हूं इसको भी, मैं बताऊंगा क्यों क्लोज ये भी ले रहा हूं। देयर एग्जिस्ट अ c इन बिटवीन सच दैट f follows hk minus 1 for all x lying in c to b, and fk follows, f नहीं फॉलो करता एक्चुअली, माइनस f follows hk minus 1 for all x between a to c। अब सिंपल सा बात ये है, अगर f जो है वो h के फॉलो कर रहा है a से b में, तो मेरा लेमा ये बोलता है, मेरा लेमा इज दैट f will follow hk minus 1 for all x belong to c and b, और वो c क्या है वो देखेंगे। व्हाट इज दिस c? c इज इनसाइड a and b। c अब मैं क्लोज इसलिए लिया हूं क्योंकि c a भी हो सकता है, c b भी हो सकता है। तो इसका मतलब एक सिंपल सा लेते हैं, अगर इफ c इक्वल टू a, अगर c a के बराबर हो गया, इसका मतलब क्या है कि जो पूरा का पूरा a to b है उसमें f h के माइनस 1 फॉलो कर रहा है, ठीक है। तो f h के भी फॉलो कर रहा है, f h के माइनस 1 फॉलो कर रहा है। अगर f h के माइनस 1 फॉलो कर रहा है, अगर मैं a ले लूं, तो क्या मैं फिर h के माइनस 2 पे कमेंट कर सकता हूं इटरेटिवली सेम चीज लगा के, क्योंकि f h के माइनस 1 फॉलो कर रहा है। उसी तरह अगर c b के बराबर हो गया तो माइनस f फॉलो कर रहा होगा, मतलब कि माइनस f इज फॉलोइंग h के माइनस। इसका मतलब क्या है? इसका मतलब क्या है? माइनस f इज फॉलोइंग दिस,
नॉन नेगेटिव, नॉन
हाँ, मतलब कि इसका मतलब ये हो जाएगा कि डेल्टा h f इज लेस देन 0, मतलब h minus 1, सॉरी, माइनस f इज फॉलोइंग दिस मींस दिस। तो अब क्या हो गया? तो मेरे पास जो दो केसेस हैं जहां पे मैं मान रहा हूं c या तो a हो जाएगा या वो b हो जाएगा, और दो केसेस वी हैव दिस केस। अब अगर मैं इटरेटिवली इस पे लगाते जाऊं तो फिर f क्या होगा, क्या फॉलो करेगा? h के माइनस 2, क्योंकि f फॉलो कर रहा है h के माइनस 1 बिटवीन c एंड b। तो मैं क्या लेना, सपोज c यहां आर्बिट्री में c को बीच में मान लिया, तो f जो है इस वाले पार्ट में h के माइनस 1 फॉलो कर रहा है और इस वाले पार्ट में माइनस f फॉलो कर रहा है। अगर f इसमें h के माइनस 1 फॉलो कर रहा है तो फिर मैं यही चीज जो सेम लेमा है अप्लाई कर दूंगा इस दोनों के बीच में। अगर मैं इसको k टाइम्स अप्लाई कर दूं, इसका मतलब मेरे पास क्या निकल के आएगा कि f will be following what? h2, f will be following h2। हाँ k minus 2 टाइम्स अगर मैं लगाऊं तो फिर मैं क्या करूंगा, f पे फिर लगाऊंगा, लेट्स सपोज दिस इज c1, दिस इज c2, फिर माइनस f पे लगाऊंगा, आई विल हैव सम c3, माइनस f का माइनस फॉलो कर रहा होगा यहाँ पे, यानी कि f फॉलो कर रहा होगा h के माइनस व्हाट। अगर यहाँ पे k माइनस 1 को फिर एक बार तोड़ूंगा तो k माइनस 2, इसको भी तोड़ूंगा तो k माइनस 2, रिपीटिवली लगाऊंगा तो मेरे पास आएगा कि किसी ऐसा हो जाएगा, रिपीटिवली लगाने क्या हो जाएगा, a b, फिर मैं करूंगा x1 x2 up to okay, so something xp है, what is p will come to p is k minus 2, okay, so wait, p will be 2 power k minus 1, why this? Because we are bifurcating every time, no, so that's why there is coming 2 power k minus 1. This is very easy to understand, बस एक बार देखना पेपर में, दिस वेरी इजी। यानी कि हो सकता माइनस एफ यहाँ फॉलो होगा H2, हो सकता है F यहाँ फॉलो होगा H2 माइनस एफ H2। तो इसका मतलब कि मैंने F का और माइनस F का जो कंडीशन है वो फॉलोइंग H2 वो मेरे को पता चल गया। तो मतलब इस तरीका से क्या हो रहा है कि मैं फिर F के ऊपर जो H2 का प्रॉपर्टी है वो फॉलो करवा दिया इन सम इंटरवल्स। जो फर्स्ट 6 लेमा जो लग जाएंगे, फर्स्ट 6 लेमा इन द सेंस कि मेरे पास ये होगा, मतलब ये तो है, ये तो जनरल है। I have I guess 3, 4, 5 and 6. I have 3 and 4, 5 and 6 in each interval. In each interval. तो यानी कि f prime x का कंटिन्यूअस होना और इसका hk-1 फॉलो करना, that is ट्रिवियल इन ऑल these intervals. इस बात आगे यहाँ तक किसी को डाउट? मतलब मैं बेसिकली जो प्रूफ का कंस्ट्रक्शन है स्टेप है वो बता रहा हूँ। अगर मेरे को हर एक इंटरवल में ये पता चल गया कि f is following H2, then by all those things except these points I'm done. किसी को डाउट? सो पॉइंट यहाँ पे कि मैं इस वाले पॉइंट्स पे क्या करूँ? पॉइंट ये है कि मेरे को यहाँ भी तो दिखाना पड़ेगा जो फाइनाइट नंबर ऑफ पॉइंट्स मेरे आए हैं, I have to so that there are also f prime is continuous or something that उस चीज के लिए बेसिकली एक लेमा है। मैं इस लेमा को ही प्रूव करूंगा क्योंकि इसका सब कुछ ट्रिक है। आफ्टर दिस एवरीथिंग इज ट्रिक ओनली, बट हियर सो लेमा इज लाइक, जैसे अपने पास एक लेमा है ना, दिस लेमा that f satisfies H2 or then therefore we have this condition. So अगर f H2 satisfy कर रहा है तो we have this condition. Any cases अगर f HK satisfy कर रहा होगा तो वहाँ condition क्या होगा? अगर f HK satisfy कर रहा है तो ये condition किस फॉर्म में चलेगा? Any guess?
The top one will be K-1.
Yeah. So that will be my K-1 and this will change to, so I'm just writing this only, my minus of K-1 and this K-1. सब समझ में मैं ये कुछ वो कैसे हो गया हाउ दिस, क्योंकि अगर वहाँ 1 H2 था तो K को 2 रख दो, तो बेसिकली ये एक केस है जहाँ पे तुम H2 के लिए फॉलो करते हो। जनरल केस में हमको वहाँ पे K रखना पड़ेगा। ओके, व्हाई डू आई नीड दिस थिंग? तो बेसिकली जब मैं ये प्रूफ कर रहा हूँ ना कि ऐसा कोई एक C एग्जिस्ट करेगा, पहली बात तो फर्स्ट स्टेप तो मेरा यही है ना, HK-1 को प्रूफ करना। तो जब मैं ये स्टेप फॉलो कर रहा हूँ तो मेरे को एक C चाहिए। तो फॉर एग्जिस्टेंस ऑफ C आई नीड दिस, एग्जिस्टेंस ऑफ C ये समथिंग। सो मतलब एग्जिस्टेंस ऑफ C के साथ दो कंडीशन है, दैट शुड बी वेरी वेरी अच्छे से उसको समझना होगा। मैं थोड़ा सा स्ट्रॉन्ग चीज बोल रहा हूँ। मैं क्या बोल रहा हूँ कि इस वाले पूरे के पूरे x में f HK-1 फॉलो करेगा। मैं ये नहीं बोल रहा हूँ कि किसी किसी पॉइंट से फॉलो करेगा। तो एग्जिस्टेंस ऑफ C इज वन थिंग, प्रूविंग दैट देयर आर सच इंटरवल, और ये एग्जॉस्ट हो जाएगा, ये एग्जॉस्ट करेगा इस पूरे के पूरे इंटरवल को, दैट इज इंपॉर्टेंट। वो और क्या केस हो सकता है? इज देयर एनी अदर केस दैट कैन हैपन? मैं फिर से अपने क्वेश्चन को रिपीट कर देता हूँ। मैं ये बोल रहा हूँ f HK-1 फॉलो करेगा इसमें, माइनस f करेगा इसमें। ओके, ऐसा भी हो सकता था कि C3 A से C3 में कर रहा हूँ, जैसे सपोज मेरे पास C3 और C2 निकल के आ गया पहले, कि A से C3 में माइनस f फॉलो कर रहा है, C2 से B में f फॉलो कर रहा है, बीच का कुछ पता नहीं मेरे को। कैन दिस बी अ केस? फिर से मैं बोलता हूँ, मैंने बहुत लेमा लिख दिया, लेमा समझना ही चाहिए, बट मैं फिर से रिपीट करता हूँ प्रॉब्लम क्या है यहाँ पे, व्हाई डू आई नीड दैट। अगर मेरे पास ये जो C निकालने का कोशिश कर रहा हूँ ना, मेरा लेमा का स्ट्रॉन्ग क्या पॉइंट ये कि मेरे पास एक जॉश हो जाएगा इंटरवल पूरा HK-1 f और माइनस f में। बट दिस कैन हैपन कि मेरे पास C3 आ जाए, C2 आ जाए, जिसमें यहाँ पे वो फॉलो हो रहा हो क्या चीज HK-1, यहाँ पे माइनस HK-1, यहाँ मुझे पता नहीं, बट दिस कांट हैपन। व्हाई? दिस कैनॉट हैपन बिकॉज ऑफ दिस लिमिट। जब मैं पेपर को डालूंगा ना तो ये सब चीज पे सोचना, बिकॉज दिस थिंग्स आर वेरी सब्टल स्टफ्स, कि आखिरकार क्यों मेरा ये लेमा ना वो इंप्लाई करता है कि वो एग्जॉस्ट हो जाएगा। लेमा 2 इंप्लाइज दैट दिस एग्जॉस्ट, और लेमा 7 जो भी मैं लिखूंगा So this is the last lemma of 9. lemma बोलता है कि अगर मेरे पास x लेस देन b ग्रेटर देन a है तो वही है h माइनस k माइनस 1 ऐसे वहाँ लिखा हुआ फिर मैं लिख दे रहा हूँ h f is non-decreasing function of h. अब ये h पे कंडीशन का निकल जाएगा पॉइंट ये कि ये जो h पे कंडीशन निकल गया दिस इज बिकॉज़ हम चाहते हैं कि जो भी मेरे पास ये निकल के आ रहा है ना जब मैं इसके अंदर आपको इसको बाइनोमियल से तोड़ दूं तो जो भी इसका आर्गुमेंट है दैट शुड बी इनसाइड ए कॉमा दैट्स व्हाई दिस आर कमिंग तो मेरे पास ये बेसिकली प्रूव करना है ओके सो लेमा 1 से बाय यूजिंग लेमा 1 मैं लेमा 1 यूज कर रहा हूं मैं बोल सकता हूं कि दिस इज फाइन क्या मैं बोल सकता हूं ये चीज क्योंकि ये जो है ये 2 टाइम्स करेगा ये k - 2 टाइम्स so this is k forward difference because we have assumed that f is following hk so this is following अब यहां मजेदार चीज क्या है अगर मैं इसमें ऐसा करता हूं कि एक समय के लिए इसको h मानता हूं लेमा 1 पे यूज करके और मैं क्या करता हूं कि h को फिक्स कर देता हूं आई एम फिक्स्ड h तो ये किसका फंक्शन है सिर्फ f किसका फंक्शन है सिर्फ f किसका फंक्शन है x का अगर मैं इसमें h फिक्स कर देता हूं तो ये किसका फंक्शन हो जाएगा x का और वो x किसके अंदर है a b के अंदर इसका मतलब है कि और डेल्टा तो मैं चेंज कर सकता हूं लेकिन मेरे पास एक अच्छा चीज क्या निकल जाएगा दिस इज फॉलोइंग h2 दिस होल थिंग इज फॉलोइंग h2 अगर ये h2 फॉलो कर रहा है तो क्या मेरे पास लिमिट जो भी अभी मैंने पॉइंट किया था 4 मतलब जो भी वहां 3 4 5 6 है मेरे पास आ गया काम में सिमिलरली मैं क्या कर सकता हूं ये इंटरचेंज हो सकते हैं ठीक है इससे क्या पता चला एक मिनट को यही है ना एक मिनट सॉरी k - 1 कर दे रहा हूं यहां पे तो यहां इससे क्या पता चल गया कि दिस इज फॉलोइंग अगर मैं यहां डेल्टा फिक्स कर दूं तो दिस इज फॉलोइंग hk - 1 ये जो चीज दिख गया अब जो मैं प्रूफ करना चाहता हूं तो बाय इंडक्शन क्योंकि मेरे पास h2 के लिए प्रूफ है ये मैं k - 1 तक के लिए मान सकता हूं जब मैं इसको k - 1 तक मानूंगा तो ये जो है वो फॉलो कर रहा होगा दैट this is also following that because this is what following k - 1 so I can apply the same thing on both so मैं क्या कर सकता हूं मैं ये करूंगा epsilon k - 1 fx upon epsilon k - 1 ठीक है अब मैं क्या कर रहा हूं कि डेल्टा चूज कर रहा हूं epsilon से ग्रेटर देन 0 तो जो यहां पे ये जो है वो नॉन डिक्रीजिंग फंक्शन ऑफ h है जैसे नॉन डिक्रीजिंग फंक्शन ऑफ h तो अगर मैं डेल्टा को epsilon से छोटा लूंगा तो ये इससे छोटा कहां चाहिए था मेरे को ये प्रूफ करना है ना अल्टीमेटली जो मेरा थ्योरम है वो ये प्रूफ करना चाह रहा है कैसे करेंगे एनी गेस थोड़ा सा मैनिपुलेशन है ये दोनों का यूज करना है हाउ कैन आई डू दिस सोचो कोई गेस कुछ भी बोलो देखो सोचोगे कुछ निकलेगा कुछ बोलो क्या कर सकते हैं देखो सबसे सिंपल सी बात है कि ये जो लिखा है इसको मैं मैनिपुलेट कर सकता हूँ इस चीज को मैनिपुलेट करता हूँ कैन आई राइट दिस लाइन ठीक है फर्स्ट स्टेप और इसमें क्या यूज करूंगा मैं अच्छा मैं बताता हूँ मैं क्या यूज कर रहा हूँ दिस इज a + 2 मल्टीप्लाई बाय e ठीक है ये यूज कर लिया अब जो ये है मेरे पास दिस इज फॉलोइंग h2 तो तुम सोचो क्या मैं इसको लिख सकता हूं ये जो है इसको मैं फिक्स करने दिया एप्सिलॉन की जगह डेल्टा ले लेता हूं ये समझ में आया कैसे हुआ ये चीज सेम ही रहा इसलिए मैंने इसको पहले बाहर निकाला अब जो ये बच गया ये इसको मैं g मान लेता हूं इस समय के लिए So this is nothing but उस लेमा का यूज करके तो ये जो मैनिपुलेशन हुआ उसको बस मैंने यहाँ यूज किया, ठीक है। अब क्या करूँगा सोचो, व्हाट कैन बी माय नेक्स्ट स्टेप? नेक्स्ट स्टेप क्या हो सकता है?
एक और
इसका एक बार बोल दूं, ये जो है ना लिखा हुआ, इसमें मैंने e माइनस k माइनस 1 से
अब डेल्टा एप्सिलॉन k माइनस 3 और डेल्टा एप्सिलॉन एक और बार पढ़ लेंगे।
ओके, सो यू वांट कि मैं इसको बाहर ले लूं पहले, तो मैंने क्या होता है एप्सिलॉन k माइनस 2 डेल्टा f, इस डेल्टा को इस e पावर k माइनस 2 ले लूं,
मतलब डेल्टा एप्सिलॉन इनटू डेल्टा एप्सिलॉन k माइनस 3 लिख दो।
हाँ। तो बेसिकली जब मैं ये लूंगा, देखो k माइनस 2 कौन फॉलो कर रहा है? ये फॉलो कर रहा है ना, सॉरी k माइनस ये फॉलो कर रहा है। ये जो चीज दिख रहा है, कुछ ये दिख रहा है, क्या ये कुछ दिख रहा है? यही चीज है ना, बट k की जगह क्या आ गया? k माइनस 2 आ गया और एप्सिलॉन है। क्या मैं इसको सब्स्टिट्यूट कर दूं? क्योंकि मैंने इंडक्शन से माना कि अगर वो k माइनस 1 फॉलो कर रहा है, ये फॉलो कर रहा होगा। दिस इज ग्रेटर देन व्हाट? k माइनस 1 डेल्टा f अपॉन डेल्टा इंटू डेल्टा k माइनस 1। हो गया? सो दिस इज, इसमें कोई दिक्कत? जो स्टेप मैंने ये कर दिया इसमें कोई दिक्कत? किसी बोलो? ओके, इसको रिपीट कर दूं? तो देखो मैंने ये क्या वाला, ये देखो ये जो चीज लिखा हुआ है इसको इसमें के लिए g मान लो। दिस इज व्हाट रिटन। और मैं अगर तो g क्या फॉलो कर रहा है? अभी मैंने बोला व्हाट इज दिस फॉलोइंग hk माइनस 1। तो फिर मैं इसको किससे बड़ा लिख सकता हूँ? इसको छोड़ देते, इससे बड़ा लिख सकता हूँ। दिस इज ओनली g, क्योंकि डेल्टा लेस देन एप्सिलॉन ना, बस डेल्टा, और ये जो डेल्टा था उसको रख दिया था।
k माइनस 2 है।
हाँ, डेल्टा इनटू डेल्टा के माइनस 2 डेल्टा के माइनस 1, ठीक है। दिस इज व्हाट, सो दिस इज बेसिकली एक ट्रिक, गुड ट्रिक आई थिंक। अगर इसको करो तो अच्छा लगेगा। उसके बाद है, इसके बाद लेमा 8 है, उसमें बेसिकली उसका c का एग्जिस्टेंस प्रूव करना है। ओके, यू हैव टू प्रूव द एग्जिस्टेंस ऑफ c। आफ्टर दैट इट्स वेरी इजी, यू जस्ट हैव टू डू द मैनिपुलेशन स्टफ। सो आई विल पोस्ट दिस ऑन द टीम्स। अगर उसके बाद भी नहीं प्रॉब्लम आ रहा है, समझ में नहीं आ रहा, तो यू कैन, ओके। किसी को डाउट है पूरे 1 से लेकर अभी तक कोई भी क्लेम है? आई थिंक okay, fine.
Or can we do this tomorrow? Can we complete the rest of the lemmas tomorrow?
Give a gap of 2 to 3 days for us.
Okay.
Like look into it
Okay.
and then come back.
Yeah, fine.
So we'll see what can be done.